Okay, so the transport layer is the next protocol layer up. So transport layers provide communication between two endpoints, between the two operating systems on either side. It supports the communication between the processes that are running on each of the end hosts. And these are basically implemented in the host OS. The two different transport protocols that we're going to cover, and the two main ones, are TCP and UDP. These are the functions that a transport layer will implement, and they're similar to the network layer. So you have a demultiplexing to the upper layer. What's the higher layer protocol that's going to handle this packet or segment? Connection setup. So if the transport layer provides a connection abstraction for the application, then you need some way of setting up that connection and implementing the connection. Delivery semantics. How are the packets being delivered to the application? What is the abstraction that the transport layer provides to the applications that are using that layer? Flow control and congestion control. How do you control the transmission of packets so that you're not flooding either the operating system or the network, etc.? And then the last one is security. So I'm going to handle the first one with both TCP and UDP because they use the same thing. And we already talked about the port number, the 16-bit port number. That's the port number that determines the local address, the local process on the host to send that packet to. So in this case, you could send it to the web server, in which case the local port is pointing to HTTP. You could be sending it to a mail server on that machine, in which case it's 25. You could be sending it to DNS, which is 53. You could be sending it to HTTPS, which is 443. So the local port number says, well, which process on either the client or the server am I going to send this packet, this segment to? And it's both 16 bits in both the UDP header and in the TCP header. Okay. So what are the services that are layered on top of it? So we saw here there's a subset: SMTP, HTTP, NTP, and DNS. The things that use TCP are HTTP, SMTP, IMAP, and POP, which are email protocols. Things that need reliability and they need consistency, where you can't have any of the bits be corrupted, those things will use TCP. Because TCP is actually going to give you reliability and integrity all at once. What uses UDP? It's stuff that doesn't necessarily need a connection or integrity. So some of this, well, DNS needs integrity, which is going to be done using other mechanisms. But DNS, Network Time Protocol, and then interactive online games are using UDP, where you don't necessarily, especially for games, you don't care about reliability. If a packet gets lost, you don't want the thing to be retransmitted, because typically in a game, you're continually sending updates from one end to the other. You're just going to have to wait for the next packet to get updated. So on any first-person shooter, for example, you're sending packets every 20 milliseconds or so. So you don't have time to do a 200 millisecond round trip time to recover a packet. You just wait 20 milliseconds and the state will get updated again. So that's why most games, interactive games, will just use UDP for that operation. Many of the protocols are going to be able to use both, and in fact, DNS can use both TCP and UDP, and we'll see HTTP is now going to be able to use TCP and UDP as well. Okay, so we talked about this a little bit earlier in one of your labs, but you can go to Etsy Services or Windows System 32 services to see all of the different application protocols that the transport layer protocol will demultiplex up into. And you see domain name, HTTP, BGP is there, HTTPS, etc. And these things are assigned by IANA. So this is a numbering agency that if you have a service that you want to bring up and you want a particular port number for it, you get them to agree to allocate that number for you, and then you can get up into this this file. Okay, so we're going to first talk about UDP because it's the easiest thing to talk about. This is the bare bones transport protocol. This is the header. And you can see all it has are the two port numbers, and it's got a length that says how big is this datagram, and then a checksum. And then all of it is, the rest of it is just application data. And so you'll see with UDP, all it does is demultiplex with the port numbers. there is no connection semantic. So there's no connection ID, there's no handshaking between the sender and the receiver. There's minimal state that is kept with UDP. You're just sending packets towards destinations and hoping that somewhere on the other side, someone's going to pick up that packet and use it. In terms of delivery semantics, there's no reliability. It's completely unordered. If you send two datagrams back to back, they could be flipped in their order on the way over there. And it's mostly unicast. There's no flow control support. There's no congestion control support. You can completely flood as many packets as you want with UDP to launch a denial of service attack, for example. You can send as many packets as you like. There's also no security. This is often used for applications that need a particular bit rate. So if you don't want to deal with a congestion control protocol, if you need 1 megabit per second, you can use UDP and then you can send at 1 megabit per second, is the idea. The other protocol that we're going to spend the rest of this time talking about is TCP, this transmission control protocol. I want to be cognizant of the time, so I have to, hopefully I don't have to talk too much about Google here. 3:39, 10 minutes, okay. So TCP is this transmission control protocol. It's more, it supports a connection. So when you connect up to a web server, what you want to be able to do is have an abstraction that is a persistent connection from you and the server. And you want to be able to send bytes to the server, have that server get those bytes in order, and then have the server respond to you with the bytes that it puts into that connection. So this is more like a telephone abstraction, right? Like the bytes that you speak into the one end get received on the other, and vice versa. You want the protocol to implement all of that. You don't want to have in your web server or your web client, you don't want to have that logic inside of your application at all. You want to rely upon this in the lower layer, the transport protocol. And that's what TCP is meant to do. Reliable, in-order, byte stream delivery of data from point to point. So this is typically a point-to-point unicast connection that we're talking about, and it's full duplex, meaning it's a bidirectional connection. So this means when you set up a connection from your web browser to the web server, there is a bidirectional connection. One side allows you to send a URL to the server, and the other side allows the server to send you back the payload, the images or the HTML. It is also flow and congestion controlled. So there is this notion that there is a pipe between the sender and the receiver, and is of a certain size. Like the link bandwidth is the size of that pipe, and you don't want the transmission to exceed that, right? You want to be a good network citizen. You want to use the resources that are available, and you don't want to blow up and cause a lot of network packet losses. So there's an algorithm to make sure that the network doesn't get blown up and that the receiver doesn't get blown up. So that's both flow and congestion control as part of this protocol. And so how is this done? This is done over IP using checksums, sequence numbers, acknowledgements, retransmissions, and then rate limits on the sender. So these are all facilities that TCP is going to take care of for you so that when you bring up your connection to a web server or a mail server, you don't have to worry about implementing all of this. So this is all done for you. And this is the abstraction that TCP is giving you. You have an application on, say this is the client, and the client wants to send some data. All the client does is write the data into the TCP layer, and then TCP is going to take care of sending this reliably over a unreliable IP network to the other side, so that on the other side, the bytes that this receiver gets are exactly the bytes that got put into on the other side. Okay, so then TCP has to take care of these particular problems. What happens if the data is corrupted? So you say get index.html, and then there's a W that gets added. And so the way it detects this is to add a checksum. So it takes all of the packets, or all the bytes in the packet, and then it adds it up to create a checksum. And then on the other side, the receiver will add up the bytes in the packet and then check against the checksum. And if they don't match, we'll drop the packet. So that's part of TCP. So you see that this packet, 4 plus 5 is 9. 9 doesn't match 7. So on the receiver will get this, and then we'll discard it. We'll throw it away. And that's done with this checksum. So you see this checksum is implementing that. Takes this whole thing as a bunch of numbers, adds them all up, fills in this checksum, And if the checksum doesn't match on the receiving end, it just simply drops the packet. What happens if the data is out of order? You say get x dot, this should be h, no. You say get index.html, and it swaps the middle two. And so how do you know on the other side what order your data was sent in by the sender? And so the way you solve this is to add sequence numbers. Sequence number 1 is get. Sequence number 2 is INDE. Sequence number 3 is x.h. That should be ht, not th. And then 4 is ml. And that's done. So this is a picture of the TCP segment, the TCP header. That's done with a sequence number. So every piece of data that you send with TCP has a unique sequence number associated with that data. And this allows the receiver to put the segments in order so that it can actually produce the exact byte stream that it was given. Okay. So in order to establish a sequence number space between the client and the server, you basically have to negotiate sequence numbers that you're going to be using. So here, this is done with the three-way handshake that starts every TCP connection. So as part of a TCP handshake, you're going to send a sequence number that A wants to use to start labeling its packets as part of this connection setup, and then B will acknowledge this sequence number A, and then we'll send a sequence number B that it wants to use for any data that it sends the other direction. And then as part of the final part, this is the three-way handshake, the last part of this acknowledges B. And at this point, both A and B know their sequence numbers that they're sending data to and from each other, and then they can then do the protocol reliably, checking for sequence numbers and acknowledgements. Okay, the next problem is what happens if the data is lost? And so if you send get index.html and some router drops it, the solution is to have a timeout, wait for an acknowledgement, and then if you don't get it and that timeout goes off, then you retransmit it. And this is implemented in the operating system. So when you send data to TCP in the operating system will turn that into a TCP segment, we'll send it to the destination, but we'll keep a copy in its operating system's buffer. And only when it gets an acknowledgement from the receiver that it has received that segment will the sending operating system discard that. And so in that way, it's able to implement reliability without the application knowing anything about it, right? It's going to keep all of the data it sends and then just discard it whenever the acknowledgement on the other side gets back. So in order to do this, it needs an acknowledgement number. It needs the receiver to say, hey, I got this packet of yours. And you need to be able to label which packet that you have currently gotten the data for. And that's what's sent back on the response. On all the acknowledgements back and forth, you're saying, I got this packet, I got this packet, I got this packet. And this allows the sending operating system to discard that packet from its transmission buffer. Okay. So in terms of retransmissions, there are two ways that the sender will retransmit data. One is through this timeout event that I just mentioned. So the algorithm is that TCP has a single retransmission timer. The sender sends the segment and sets that timer. And if no acknowledgement is received and the timer goes off, it will immediately resend that segment. Okay? The timer is based on a measured round trip time. So you only want to retransmit packets that you can be sure have been dropped. And so what TCP will do is it will try and average the round trip time between the source and the destination. And if you have exceeded the average round trip time plus 2 times the standard deviation of the round trip time, then you can retransmit that packet. So it adapts based on the latency of your connection that it has observed. Okay. And I think I am out of time. Well, close to out of time. The last, I'll do this and then I'll end. The other way, there's a second way of doing a retransmission. You can be a little bit more intelligent with your retransmission. If you send packets 1 through 5 to the receiver, and the receiver acts 1, 3, 4, and 5, the sender can just infer that packet 2 got lost and retransmit this immediately. And so this fast retransmission is something that we'll talk about next class. Okay, so we're going to continue our run up the protocol stack up into cloud applications. We're at TCP, and we're going through some of the abstractions that TCP gives you and how it implements those at a fairly high level. We got all the way out to reliability, and we talked about the sequence numbers and the acknowledgments that come back to make sure that the packets that you send are received on the other side. There are two ways that a sender will retransmit a packet that it hasn't received an acknowledgement for yet. So the sender is going to send that, keep that packet in the operating system until it gets an explicit acknowledgement back for it. If a timeout occurs, that's when it will know that, okay, I need to resend that thing. It can resend things more aggressively if, for example, there's a gap in the acknowledgement numbers that it receives back. So if it gets packets 1, then 3, then 4, then 5, then it just infers that 2 is lost. Okay. The next thing that TCP provides you is this facility. What happens if the receiver has no more resources to sync any of the packets that the sender is sending? So in this case, we want to prevent the sender from flooding the receiver. And so here's an example. It used to say remix.mp3 when MP3s used to be a high bandwidth application. So I had to change the 3 to a 4. So now it's a video. Hopefully it's an ultra HD video here that you're trying to send from the sender to the receiver. The solution is to do something called a receiver advertised window. The way this works is on the receiver's operating system, there is a buffer for every single connection that it has on the internet. And this buffer is handling packets from IP coming in, and it is storing it to be read by the application process. So maybe you've got a Netflix stream going on and your client is receiving your episode in its operating system buffer, but then the video player has to read from the operating system buffer in order to render your video. It's going to take a while. The Netflix application, the video application, might not be able to read it fast enough. And if it is the case that it falls behind, what's going to happen is that this is going to fill up. And what you don't want to have happen is for this to fill up and then incoming packets be dropped because there's no space, because that would disrupt the transfer. And so there is this space, the spare room in the operating system buffer for new segments to be received. There is some space here that's called the receive window. And so it's basically the size of the buffer minus the size of the data that's currently being queued for delivery to that receiving application. And so this window is advertised from the receiver to the sender every acknowledgement. So every acknowledgement going from the receiver back to the sender will have this amount of space in this buffer sent as an integer in the packet header. So that's how it does. This is considered flow control in TCP. The other thing that you want to take care of is what happens if the network is overloaded. So we don't want to overload the receiver, but we also don't want to overload the network, because if we bomb the network, we're going to get a whole bunch of packet loss as a result of doing packet switching. We do want short bursts of data to be buffered, so we do want to allow some kind of burstiness in what we send, but if it's persistent overconsumption of bandwidth, we want a facility to tell the sender to slow down. And this is called congestion control. And the goal for TCP congestion control is to do two things. Prevent spurious retransmissions of packets still in flight. So if you send a packet and you're like, hey, I haven't heard back an acknowledgement, you don't want to resend while that thing is still being delivered, right? Because then you're sending multiple packets for the price of one. You want a reliable way of only retransmitting when you know a packet's been lost. So that's the first one. The second one is you want to reduce the number of packets that you send that get dropped later on in the network. Because when you send a packet and it makes it, for example, halfway through the network and then gets dropped, all of the resources along the way have just been wasted. And if everyone is doing that, you've got no progress on anyone's connections, right? But you've got 100% utilization of all the resources in the network. So you want to be able to avoid that. You want to minimize the total number of packets lost in the network. And so what TCP does is it keeps a window, a congestion window on the sender. And this is in the operating system of Linux or Windows or any of the operating systems that you have. There is this number called the congestion window, and it's kept per connection. Every connection has got this variable, cwind, and it's basically used as an estimate for how much that connection can handle in terms of bandwidth. And this estimate will increase whenever packets are delivered. Anytime packets are getting delivered fine, the sender's going to be like, you know what, the network can handle more. It's going to be greedy. It's going to try and send as fast as it can. Anytime it sees a packet loss and has to do a retransmission, it'll cut the transmission rate in half, or it'll slow it down, the congestion window. So the size of the window denotes how much a network can absorb, and it's considered, we call it the size of the pipe. Ideally, it will be the bandwidth times the delay product of the connection. Okay. So the goal of this algorithm is to make it as large as possible without a loss. And because you have both a flow control mechanism and a congestion control mechanism, the sender is going to send at a rate that is the minimum of the two. You have a flow control window not to overflow the receiver. You have a congestion control window not to overflow the network. Your actual sending rate has to be the min of both of those. So that's the algorithm. Okay, so I'm going to briefly talk about how TCP used to work. It no longer works this way. So in the networking class, you'll probably learn all about this. But now we've gotten to a point where we have a whole bunch of different windowing algorithms in use today. But it used to be the following mechanism. Right when you started a connection, you did something called slow start, which basically implements exponential growth at the beginning. So you're like, that's not slow at all. In computer science, that's like anything but slow, exponential speed up. But this is slow compared to what TCP used to do. TCP used to just burst out the entire window size as soon as it could. So if your window was 100, it would just send 100 packets immediately when it could. In this case, the TCP window starts at 1, and then every round trip it'll double as long as no packets are lost. So that's the rate. Whenever a loss finally occurs on that connection, then you can infer that because you are doubling every round trip time, the window size is somewhere in between half of W and your current W. And so on a loss, TCP will just have the window size. And that's a result of its slow start algorithm that was doing the doubling. When you have the congestion window, now you want to be a little bit more conservative in terms of how you probe for bandwidth, because you know it's in that range. And so what it'll do is it'll add 1 to the congestion window every round trip time rather than doubling it every round trip time. And this gives you linear increase or additive increase. So what you'll end up getting for TCP congestion control is a picture that looks like this. When the connection starts, it exponentially ramps up. It gets a loss, gets its first loss here. It halves. So this is meant to be half. It's a little skewed. It halves the congestion window, and then it linearly increases it by 1 every round trip time. And then when it gets another loss, it'll do the same thing, half and then linearly increase. So this is the algorithm as it used to be in the 90s. But this algorithm had some issues. The first one is that short transfers, which is a lot of transfers as it turns out. When you're sending small HTML pages, they're pretty small, or small icons. The amount of packets that you're going to send on a transfer is going to be quite small. But your congestion window always starts at 1, right? So I need that thing to do multiple round trip times before I can get my little icon, which seems crazy, right? That's a lot of delay. The other thing is that if I do get a packet loss on a short connection, I talked about the retransmission algorithm is like if I see I have 1 and then 3, then 4, then 5, I can aggressively retransmit 2. But if I only have 1 and then 2 is lost, I don't have multiple packets in the pipeline to say, oh, I better aggressively retransmit too. So you end up stalling on a short connection that gets a packet loss, which is also not ideal. And as it turns out, the congestion window starting at 1, the reason why we picked that in a particular size was because back when this was developed, it was in the 1980s, and we were dealing with 56 kilobit per second modems. And we thought, or the designers thought, that an initial sending rate of 20 kilobits per second was actually quite reasonable. But if you look at what a cable modem, our last hop, is actually doing now, it's 1,000 times that. So maybe we should start with 1,000 times of the window size to accommodate for that. Turns out we're at 10 times. So our initial congestion window that's been approved by the standards committee is 10. And you can see this on Linux. You can configure this in this header file. And if you want to do 1,000, you can just recompile your Linux kernel to say, I want the initial congestion window to be 1,000, and then you can just go for it. Go with 1,000. But the idea is that here you have enough packets in that initial transmission to get an entire HTML page sent in one round trip. And potentially with very little loss, assuming that this is actually a reasonable bandwidth between the sender and the receiver. Okay. The other issue with this sawtooth algorithm, which is often referred to, is that it requires a really tiny bit error rate when you have a large W, so a large window size. So here's a picture of a sawtooth that goes between 50,000 SW and 100,000 SW. And if you look at the packet loss rate that's required to support this, in between these two windowing events, the packet loss events, so you are allowed 2 packet losses between these 2 points. And the number of packets that get sent in between these 2 points is basically the area under this curve. So you have the window size here and then round trip times on the bottom. And so you're basically saying you get W packets the first, so assuming W is 50,000 initially, then you send 50,000 packets the first round trip, 50,001 the second, all the way up until 100,000. And then that's the total number of packets that you have to send without any packet loss in order to support this sawtooth. But if any link along the way manages to have a bit error that causes a packet to be lost, even though it's not congested, TCP thinks that that's congestion, because any packet loss is assumed to be congestion with TCP. And then you end up with you need a bit error rate that's basically no losses in 15 billion packets, which no link can support at this point. So then you're ending up with persistent underutilization of your network for a large network, which is what we have going on right now. Okay, so the other issue is that the time it takes to grow from W to 2W, this is on the order of an hour when you're talking about maybe a 200 millisecond round trip time. In order for you to grow from half of the link bandwidth to a full link bandwidth, it takes you an hour and a half in this estimate. So most of the time, you're underutilized. In fact, you're averaging 3/4 of the full link bandwidth doing this. Okay? So this is not optimal. So in order to address this, one of the solutions from about 10 years ago was to do this thing called TCP cubic. So all of you have, I don't know if you remember this from math, x cubed. You remember the curve x cubed? Well, this is basically x cubed. You start, anytime you have a congestion event, you have the bandwidth, and then from the halving, you basically use the cubic polynomial to increase the rate up towards where you were before. And then from there, you then do a cubic growth afterwards to try and probe for new bandwidth. And so the attempt here is to try and get that thing as close as you can to the bottleneck bandwidth at all times, is this algorithm. And this was used initially in QUIC, and then any TCP stack for Linux beyond 2.6.19 used this algorithm. And this is what it looks like. Rather than the sawtooth, you can sort of see the cubic thing happening, where it goes almost right back up, and then it does a cubic increase further along. So that is potentially going to give you a better saturation of your bottleneck link if everyone uses this. Of course, if you're the only one who uses it and everyone else is using the slower algorithm, you're basically going to drown them out of their fair share of the network. And then, well, people don't know it at this level. They won't know to be mad at you, but they'll be unhappy with the network and not know why. But you'll know why. Yeah.
Yeah, I was wondering, so for the C-WIN, it's basically just so you don't overwhelm the network for everybody else. So, like, yeah, what's to stop you from just, like, setting your C-WIN, like, super high?
Nothing.
You're not going to overburden the network for yourself.
Oh, yeah.
Just your individual action, right? Or isn't it, like, don't you have the cumulative effect of everyone to overburden that?
But, like, if you hog the network and everyone is backing off, then, yeah, you could actually, if you ignore congestion signals and everyone else pays attention to them, then, yeah, you can grab a larger share of the network. I was on jury duty once, and the network was really slow, and I was thinking, maybe I should crank up my congestion window and then, like, own their network, get most of their bandwidth, and then send anyone off. But, yeah, but it does require, I mean, this is an algorithm in the operating system, so it does require that you change the windowing algorithm is an operating system. For TCP, at least, it's implemented in the operating system. But, yeah, you could plug in your own congestion control protocol that basically ignores congestion, and you would be able to get more bandwidth than everybody else. You can set C-WIN as well to be as big as you want and not even do congestion control. But then you have to know what you're doing, because then if you're basically, there's a point where you'll actually get worse performance. You have to understand where the packet losses are happening and whether that impacts you. So you want to minimize your own packet loss while maximizing your bandwidth. So you have to be careful with how you set the congestion window. All right. But definitely this is something that you are, you know, this is like the tragedy of the commons sort of thing. If everyone does the exact same greedy, messed up algorithm, then we're basically hosed. The network is hosed. Unless we do something else, which I'm sure Portland State, OIT, will figure that out and be like, okay, that thing is pegged at a gigabit per second. I'm going to go to that dorm room. You know, what are you doing? If it's a dorm room. It could be my office, and then I'd be in trouble. Okay, the other solution that Google is trying is BBR. And one of the things that they did, I'm going to talk about quick sooner or later, probably next class or maybe later this class, they decided to make congestion control pluggable, where you can try out your own congestion control algorithms and see which one works best for you. They have this thing called bottleneck bandwidth and round-trip propagation time, where you're going to use the history of the network and your prior network performance for that connection as feedback to what your algorithm should be going forward. And they want to apply machine learning on that, because a machine learning algorithm can much better predict the future if it's given enough accurate historical information in the past. Whereas an algorithm like cubic is only relying on just the last congestion event to do its growth. But if you know, like, hey, you know what, yesterday or last week at exactly this time, I got 2 megabits per second, well then maybe this week at this time, I'll get 2 megabits per second. So maybe I can actually just guess and then go from there. So they're talking about using machine learning to detect that. If I have a connection history profile, over time, I can use that as my congestion control feedback. That's not yet implemented anywhere. They're just suggesting that. They're suggesting that all of the CS algorithms that we're doing could be replaced by these statistical pattern recognition things, these machine learning algorithms. Like, they're talking about inside the operating system, replacement policies and caches. They're talking about all of those, pulling out the algorithm that's there, and then doing some kind of machine learning on based thing. Okay. All right. So the last part of the transport layer protocol is the security part, and I kept this separate because this takes a whole lot to talk about. There's a whole lot here, and this is SSL and TLS. So with TCP IP security, there was initially no support for secrecy. That means everyone can see your packets. There was no support for server authentication. It means anyone could set up a server and pretend to be someone else easily. if they can hijack the network address of that person. Anyone could do a man-in-the-middle attack, sort of inject themselves into the middle of a connection and mess up the message integrity of your connection. So all of these were not taken care of, but they were really important, right? If you're going to do e-commerce over the internet, you better make sure all this stuff is supported. And so Netscape in the early 90s established this secure sockets layer to put a layer of encryption and security on top of the TCP socket layer. So it was bolted on between the application layer, your web server, and the transport layer. So between L5 and L4. And it later morphed in the early 2000s to something called transport layer security because they wanted this to be applied at the transport layer across all protocols above it. So when we run the HTTP protocol over TLS, this gives us our HTTPS URL. And the folks that support this library are there in openssl.org. And initially, the adoption was really slow, especially in the early 2000s. Only sites that actually did e-commerce were deploying the protocol. There was a lack of incentive for it to be deployed on just random regular servers, like for example, my course webpage. I don't care if that's sent in encrypted or not, it's public anyway. The other thing, and this was actually the most damaging thing, it was really hard to obtain these things called certificates. You needed someone to vouch for you who had a master signing key for you to get something that allowed you to do HTTPS. And of course, you know, I'm cheap. I don't want to pay someone $80 to sign a certificate. And I'm not doing any e-commerce on it. So I never secured my website until it became easier. And eventually, it's ubiquitous because it became easier. The first thing is that there's now hardware support to make these operations really fast, to make the public key operations that we're going to talk about in the next couple of slides really fast. The Edward Snowden surveillance revelations in terms of what was attempting to be collected on the back-end systems between content ISPs and content providers, that was enough to really force the issue on a lot of websites to add TLS. And then one of these, the biggest one, for me at least, was Let's Encrypt in 2014 started allowing you to get TLS certificates for free. And we'll talk about what Let's Encrypt is going to do to allow this. And this will be one of your labs. You'll set up an ephemeral DNS name for yourself, and then you get a TLS certificate issued so you can set up a secure website. Okay, so in order for me to explain what's going on with TLS, I need to talk about different styles of encryption. The first thing is symmetric encryption. So this, the symmetric encryption algorithm is fairly easy. It's got three main algorithms going for it. It's got a key generation algorithm that produces a random key. It could be a random number generator as part of this. And this key is the thing that you keep secret. And then if you have a message M and you want to encrypt it to produce a ciphertext C, then what you would do is you'd call the encryption algorithm with the key on the message, and it would generate your ciphertext. And then for a symmetric algorithm, to decrypt this, you would take the key and the ciphertext, and that would produce the clear text. So you're using the same key to both encrypt and decrypt. Some examples: AES, Salsa 20, Cha-Cha. Those are different kinds of symmetric encryption ciphers that are in use today. The big problem with symmetric encryption is it's got this key distribution problem. How do I get this key shared between the server and the client? Like I'm trying to set up a symmetric key encryption scheme with myself and Google. Like, do I call them to get a secret key over the phone? They don't want that. But how do I establish that? Because if I send it over the network, someone's going to be like, oh, I see that key. I'm just going to use it. So then your encryption doesn't work. So how do you get around this? And the way you get around this is with public key, private key, or asymmetric encryption. Asymmetric encryption has, again, the same three main algorithms: key generation, encryption, and decryption, but it also supports digital signatures and their verification. And this is what we will need to establish certificates over HTTPS. It uses different keys to encrypt and decrypt messages. Anyone can encrypt a message using a public key, but the owner is the owner of the private key that corresponds to that public key is the only person who can decrypt it. Okay. So these are some examples. The issue with asymmetric encryption is that it's really slow, and it's really hard to accelerate, and it's really good for a tiny amount of data. It is not good for streaming videos like Netflix over the internet. You would never use this to stream a whole video, but it's really easy to distribute a public key. You just put it up somewhere, and everyone can access your public key. You encrypt with that public key, and then only the person who has that associated private key can decrypt it. Okay, so we're going to go through some animations for how this thing works. The public key in these animations is always going to be blue. The private key that's associated with this public key is red. We're going to have some plain text and some ciphertext, and those are the icons I'm going to use. So we'll first talk about encryption. So Bob is the person who wants to be able to get messages encrypted to him. He uses a key generation algorithm to generate two keys, the private key and the public key. So this is his public, this is his private. And then he advertises his public key to Alice, which is over here, distributes that widely. Alice, if Alice wants to send a message, a plain text message, Alice will take the key, the public key, the message, send it through the encryption algorithm, and generate the ciphertext here. And then sends this payload over to Bob. Only Bob, because Bob has the private key, only Bob can turn this ciphertext into plain text. So that's encryption. Are there questions about encryption? It's often used for digital signatures. So that's the main encryption-decryption part. This is also used to do signing of data. And so the public key supports digital signatures, and then there's an associated verification algorithm that allows someone with the public key of the signer to validate that that signature came from that particular private key. So that's the other part of it. So here's a message Bob wants to send to his bank. So Alice is his bank. Bob wants to say, withdraw $1 from my account. So he has this message, withdraw $1. He takes his private key and the message, and he signs the message with this key. And so this is the signature here and the original message. So they're both packaged together and sent to Alice. Alice takes the message and the signature associated with it, gets Bob's public key, and then from this verification algorithm can say, yes, that came from Bob's private key. Bob's private key is the only key that could have sent this signature with that message. Okay, that's a digital signature. Are there questions about that abstraction? Okay, because then Alice can debit Bob's account. Okay, so one of the things with public key cryptography is that it's super expensive, and so you don't want to sign something that's enormous. So typically what is done is that you have some data that you want signed. You would take a cryptographic hash of this, send it through SHA or not MD5, SHA-256, for example, and that generates a tiny hash, and then you would use the private key to encrypt that hash, and that's considered your digital signature. And then you would attach this to the original file that might be huge, and then on the other side, you would take that data file, you would do the hash over again to get this hash value, and then you would take the signature and the public key of the associated public key for this particular sender, and you would verify that that digital signature ends up with this hash. And then if they both check out, then you can say that is authentic. That came from this signer. So this is how you get authenticity of a signature using private key cryptography. Okay, does that make sense? Do you have any questions? Because this is an abstraction that we're just going to use for from here on out. Yeah. So so the flip operation is that only the private key can generate a digital signature such that the associated public key can decrypt it into that hash. That's the main abstraction that you have here. Only this private key can give you a signature that, when used with this public key that has been advertised previously, will pass the verification algorithm. Okay, so typically you would want to use both asymmetric and symmetric key encryption together. The idea is that you want to avoid the asymmetric operation as much as you can, and you also want to make sure you solve the symmetric encryption algorithm's key distribution problem. So what is typically done, and the way you combine these two to actually get something you can use over the internet, is to use asymmetric encryption to establish the secret key that you then use for symmetrically encrypting the subsequent data. So that is the protocol that we're gonna talk about now. Okay, and then you would use that symmetric encryption key for any large-scale data transfer. So like Netflix, that's using a symmetric key encryption, but it has to do some asymmetric encryption at the beginning to set up that secret key. Okay, so an example of this is PGP, Practical Real-World Encryption. This was used to secure email. It's still used. I don't know how prevalent this is anymore. Did any of you use PGP here? No, this passed by this generation. This used to be the old school way of doing it. So this has an interesting way of combining the two. So the goal is to, in this case, we'll implicitly say Alice wants to send a large message M to Bob, and she knows that Bob has a public key over there on the right. What she'll do is she'll generate a random symmetric key. So a random number generator, and this is the symmetric key generation algorithm that she runs. And then we'll take this message M and encrypt it with that key that she generated, and generates the ciphertext for that message using the symmetric encryption key algorithm, and then encrypts the key with Bob's public key, right? So that's the very first thing I mentioned in the asymmetric encryption. She wants to send something that only Bob can decrypt, so she's going to take K, encrypt it with the public key of Bob, send Bob this ciphertext C sub K. So two ciphertexts here. The first one was encrypted with the symmetric key. The second one was encrypted with this asymmetric key. Okay? With this asymmetric key, I should say. So then this is using the public key of Bob to encrypt the key. And then sends both of those to Bob. And then what Bob's going to do, he's going to take his private key and decrypt C sub K to get the original symmetric key that Alice used. And then from the original K, uses K to decrypt M, and then now has the authentic message. Okay? Are there questions about PGP? This is at a really high level, obviously, but that's really the crux of PGP. Question: how do you securely obtain someone's public key? How did Alice get the public key of Bob? Right? Like Alice needed that. How did she get that with PGP? Anyone have an idea? How would you get that? Yeah. Publicly. Post it on the internet and hope that nobody has hijacked that connection, because there's a bootstrapping problem.
What does it matter if someone else sees your public key?
Is it Bob's public key? I can impersonate Bob and say, oh yeah, I'm Bob. I see Bob put his public key up there, and I'm like, I want to be Bob too. I'll be Bob too, and that's my public key too. Or I can send a different public key out there. Yeah. But you're on the right track publicly. You could do a trusted third party. You could have someone vouch. Yeah. So this is what the public key infrastructure is asking you to do, is to have a root of trust. that is delegating trust downward, and then eventually some delegate is going to vouch for your public key. That could be one thing. That's what they're talking about with securing BGP. You know, those BGP fake route advertisers talking about, we need a PKI to vouch for who can send route advertisements onto the internet. Of course, that hasn't happened. DNSSEC is the same thing. I need a public key infrastructure that is signing certificates and vouching for people to issue these things. So as it turns out, and of course, I'm not expecting any of you to have seen this, you used to give these away in your business card. So like here is, and sorry, you can't really see this, but this is Marcia Hoffman, and she puts her PGP fingerprint on her business card. So a face-to-face interaction, and say, I'm going to give you my business card, this is who I am, and hopefully you're going to exchange cards, and you have a PGP key as well. So then I have her BGP key, or PGP key, she has mine, and now we can send email to each other using PGP email software, and really be sure that, yes, no one is in between hijacking the content or the identity of that. This is the PGP key done as a QR code. So there's services. This is an image off of a service that will print you a business card with a PGP key on it. You could actually try and scan that from the slides and see what the key is, and it should look like that. Okay, but you have to exchange yours, so you can't just get this and then hope for a mutual authentication. You have to make sure that you're exchanging with the other person, so that both of you can authenticate each other in this communication. Okay, that doesn't work for the web. Google doesn't give me a business card with their public key on it, right? So how then do I get Google's public key? How do we get Google's public key is the question. We need to do something else. And so the question that HTTPS needs to answer is, how does Alice and her browser, how does she obtain an authentic copy of Bob's public key? And it's done using the certificate authority. And this is the trusted third party that you would need to vouch for the validity of someone's public key. So HTTPS does have this implicit trust hierarchy that's been established, and it's established through something called the certificate authority. And so here is Alice running a web browser, trying to authenticate that the server she is talking to, bob.com, is a legitimate bob.com. Like when this particular server says that this is my public key, she wants to be sure that that is actually bob.com and that is actually his public key. So that's what she wants. And there's the certificate authority. And so the way it works is that the certificate authority has a public key, private key pair. And the private key, it better keep secret, otherwise we're all hosed. So this is a secret, and then it distributes the public key widely. And in particular, it's going to distribute the public key into operating systems, into browsers, and into web servers. Everyone's going to know the public key of this certificate authority. And then what happens is that Bob wants to be able to deliver his website using an HTTPS link. It says, you know what, here is the public key I want associated with my domain name. I want you to sign this with your private key, and I am going to provide some kind of proof that I am bob.com. And it used to be that you had to get the person from the certificate authority to come to your address and for them to validate you are a legitimate company with legitimate people running the company, and then they would sign your certificate. So no one's going to want, I'm not going to have that be done, because then you pay for the person to come out, and that's where the fee goes. That's why you're paying money. You have to pay someone to validate that, yeah, you are a legitimate business doing this, so then I'm going to issue you a key. So for Let's Encrypt, all that Let's Encrypt is going to do is the proof that you need to provide to Let's Encrypt is ownership of this DNS record, bob.com, and that you own the IP address that it points to. And so what it's going to do, and you'll do this in your lab, it's going to put some secret inside of the web server that basically proves that it can control the DNS record and the IP address that it points to. And then Let's Encrypt will actually sign your request for this certificate. And it will generate the certificate for you to use. Okay? So then the next step, so after the CA validates the proof that you are bob.com, it issues your certificate. And this certificate says that bob.com's public key is this, the one that he gave, and it's attached with a signature from the CA. And then when Alice goes back to get bob.com, Bob is going to present this certificate, and Alice is like, okay, well, this certificate looks fine, but I want to validate that. I want to make sure that the certificate authority actually signed that certificate. And lo and behold, because in my browser I have the public key of the certificate authority, I can verify the certificate. Okay? Did the CA vouch for Bob? And if that certificate is legit, I'm fine. And then I get the nice green lock on my web browser. Okay. Questions? Yeah, we're going to get there. The next couple of slides, actually. Any other questions about the mechanics of how this works? Yeah, there's a lot of holes. I encourage you to take an adversarial analysis of any of this stuff. But yeah, we'll talk about that. In fact, now, so I wanted this animated, but how many certificate authorities do you think there are in your browser or in your operating system? Anyone have a ballpark? How many of these things are running around? Like, can I be a certificate authority? I'm a pretty legit person, I think. Like, can I just ask? You know, like, hey, Chrome, you know, I just learned public key. Can I sign some certificates for you? How many do you think we trust? About 100. Yeah, there's about 100 of these things. And do you feel safe trusting them? And so one of the exercises security people like to do is to go and see who they're trusting. Who is in my certificate authority store on my client? And of course you can do this. So if you could actually do this now if you have your computer. You can go to your browser, Chrome, or even, I don't know where it is in Firefox and Chrome, you just go into settings. And in settings, you go into privacy and security, and there's this thing called manage certificates. You click on that, and it brings up the local operating system certificate authority store. And so Chrome will actually use the operating system store. And in this case, this is done on a Windows machine. And you can see there are the root certificate authorities that you trust. So for example, we trust Equifax, and Equifax has always been shown to be secure. So we're going to trust all of these folks with signing authority over any of the certificates that we receive from the internet. So anything that's signed by these folks, we will just accept as being good and then give you that green lock on top. Okay. So I want to go through a little bit of the details of what is going on in the handshake to validate this. And this is the TLS protocol. So the first thing is the client says hello, and this is, so it's going to show you the way of bootstrapping a symmetric key using the certificates, the public key stuff. Just like we just did with PGP, we have to do the exact same thing using TLS. So this is the way it works. Client hello. There's some random number and the cipher suites that the client supports. So all of the symmetric encryption algorithms that the client supports is going to be advertised because they have to agree on a symmetric key algorithm to use, not only the key to use, but the actual algorithm to use as well. So that's what this thing is doing. And then the server responds with its cipher suites, some server random number, and then the certificate, as we saw in the previous slide. And then the client is going to verify that that cert was signed by the CA. So that's why the blue CA cert is there. And then the client is going to extract the public key of Bob from the certificate, and then it's going to use this public key to encrypt a master secret with the key. And this is similar to PGP, right? I want to encrypt something that I can then use to do the main work of the encryption back and forth between the sender and receiver. And then I will send that back. So this is the client trying to establish a key with this master secret encrypted with the public key of Bob. Bob decrypts this master secret with his private key, since he's the only one who owns it. generates some another key and some random numbers, and then exchanges that with the client. And this, after this handshake, you now have the ability to send encrypted messages back and forth using a symmetric key algorithm. Okay. This is incredibly slow. So this is why the server, so if you look at who does the work, most of the work, the hard work, is done on the server. And this would deter people from deploying HTTPS if they don't have the hardware to support a whole bunch of connections trying to do this. Okay. All right, and then you have your HTTPS data below. Okay, so there are some issues here we're going to talk about. The first is that it's computationally expensive, and you've got multiple round trip times. Every time you do, like you get the base page, you see that there are some embedded objects, and then you have to do the handshake again. You get another base page, and you see the objects embedded, and you have to do this every single time. So one of the things that they've talked about is TLS 1.3. There's this notion of fast open. And the idea here is to establish a cryptographic key between the client and server that acts like a cookie, like a connection cookie, so that I don't have to reestablish identity every single time. I already established it once. I'm going to embed a cookie that both the server and the client share, so that the next time I need an HTTPS connection, they'll just start the thing back up. This is similar to what you just did with your Git repository. Like, you know what? Here's my SSH key. Don't bother me with the username and password anymore. It's the same idea with this. Okay. So this, being able to send to the server without having to do this negotiation every time, this is the basis of TLS 1.3, and this is going to be the basis for a 0 round trip time handshake in Quick, which is going to follow. Okay. So the result of all of this is that eventually you can get a certificate that allows you to hit your website and then get this secure lock next to it. Okay. Okay, so we have a lot of issues here to cover because what happens if somebody reserves Oregon CTF with a 0? Can they generate this? The answer is yes. We have conflated the UI and this green lock to mean both security and identity, to support secrecy and identity using both using the same interface. So this, even though it might be a malicious site, this has a green lock because it does in fact own Oregon CTF with a 0. Okay, so that's one issue. We unfortunately have trained everybody to believe the green lock provides both secrecy and authenticity. So that's a problem, when in fact all it's doing is providing you secrecy in this case. The S and the green lock was viewed as a tacit guarantee that the site was trustworthy. And so adversaries are thinking, hey, I can pull one over on everybody who thinks this, and this is what they're doing. So Let's Encrypt is now being heavily used for phishing attacks. Because if you are sent a link that's got HTTPS, you now believe that that's actually legitimate. That would never be malware. Or that would never be a phishing attempt. I'm going to click that thing and enter my credentials because I'm going to make sure I have the green padlock. So that's a really big problem. It's like, this is from this summer actually. So this is what's happening with Let's Encrypt. And the real life people are falling for it everywhere. All right. So here's a report from FireEye from earlier this year, and there's been a 26% increase in the use of these HTTPS URLs that are malicious. All right. Here's another issue. Is this 2 browser windows or 1? I don't even know. Like, you can't tell, right? Like, this is a sneaky attack where you can overlay any screenshot or any image on top of something else that might be illegitimate. And if you're focused on this thing, you're like, wow, that looks really legit, right? Like, it does look like it might be a screenshot of the actual page, right? And then the UI around it, if you look at the UI around it, I'm guessing this is not legit, but it's paypal.login.com, and it's brought up something in the middle That's not. But you could see how this could get people to click on stuff, which is what they want. Issue number 3, and this is what Michelle was referring to. What happens if the CA is compromised, including that private key? And if you look at the expiration dates on how long you trust these keys, I don't know if I'll point that out in this UI, just because it's funny, or not. If you look at this, some of these folks we trust until 2030, 2029, 2030. So yeah, we're trusting that thing. Now, obviously, your Chrome is going to update and update that thing long before, like if it gets compromised. But like if you're running like Windows XP and you haven't patched it in like a couple decades, then yeah, you might actually have a bogus certificate that's got has a compromised signing key associated with it, and then you would believe that whatever you're getting is authentic from the other side. And this is actually how we delivered some malware to Iran, was to trick the software update thing by compromising a certificate. So this is actually what nation states are doing to each other, is compromising their certificates to bypass software updates, or to actually hijack the software updates. Okay. Okay, so this has happened. 2011, 13, 14, 15, there are probably even more, but I think I probably did this slide a couple years ago. This these things are being hijacked all the time. And if you are a hacker and you want the highest leverage point, you would go after these trust doors. Because if you can unlock this kind of trust door, you have a pretty good position. And so there have been cases where rogue nation states are trying to own certificate authorities. So they're big targets for attack. And the problem here is that you can have a rogue certificate authority that can start minting certificates for every website on the planet, regardless of whether or not they legitimately own that. Okay, so this enables a man-in-the-middle attack. As soon as you compromise the private key of the certificate authority, then you can do this. You can get the certificate authority, the key, to mint you a bad certificate. And part of that, hopefully you can read that. This is the bad guy certificate. That's sort of, I should make that gender neutral. Bad person certificate of bank.com. So I get that person to sign bank.com, even though bank.com has a legitimate one. And this is the attacker, is going to get that certificate for bank.com, and then it's going to hijack the DNS request. And when we cover DNS, we'll show how easy it is to hijack DNS. And then when this person gets bank.com, the attacker will take the request, take the SSL handshake, and then just forward the SSL handshake onto bank.com. Bank.com issues bank.com issues their server certificate, and then the attacker will just send his or her certificate back to the client. And then the SSL key exchange can be done pairwise. The attacker can do it to the victim, and then the attacker can do it to the bank, and then they can do separate key exchanges. And then all the attacker has to do is just forward the packet, decrypt it, re-encrypt it, and then you're in the middle. You can get all the transactions. Okay? So this is why having a compromised certificate authority allows you into all sorts of things you probably shouldn't be into. Okay, so that's bad. This is actually the GCHQ Flying Pig program. This is what they were doing. So this was part of what Edward Snowden revealed, that GCHQ and the NSA had a program, I forgot the name of it, that was partnering with them for targeted interception of communications. You would do this, where you would quietly do a man-in-the-middle using the certs that were going to show up as legitimate to a user. And the user has no idea. They're just looking at the UI. No one is actually poking through the signing chain of a certificate authority to say, oh, that wasn't the certificate authority that signed google.com last week. Nobody does that. So that's how you can slip by someone's security. Okay, so there are some, yeah. Yeah, I forgot what that one was, but yeah, you could post that link if you find it. Lenovo has done some pretty sketchy things, so I wouldn't put it past them. I'm using a Lenovo. But yeah, they have done some things. They've like installed rootkits on their install media. That they've done that, so it wouldn't surprise me. But I don't know. Remember that particular event. So there are some solutions to this. There's this dynamic HTTP public key pinning that allows you a website to declare the certificate authority that should be signing for it. And then on subsequent connections, the browser is going to reject any certificates that are issued by any other CA. So Facebook says my blessed authority is this one. If you see a certificate that is mine, that comes from that is signed by other certificate authorities, just reject that. And then the browser has that facility to turn it away. I like this acronym TOFU. This is trust on first use is the acronym. And then you would not trust the things that are subsequent that are different. Another thing that is being done is certificate transparency. The CAs must advertise a log of all the certificates that it's signed into a public registry, and then everyone can see the certificates being signed. So if someone hijacks a certificate authority and starts signing certificates and not updating that log, people will know immediately. Because if you get a certificate from someone and it hasn't shown up in that log, you know that's rogue. So that's what they're trying to make it open. And so any company can look at the log file on the certificate transparency site to say that, yes, this is the origin and this is when the certificate was issued. And this is what they're talking about. If you're taking the blockchain course with me this quarter, they're talking about certificates on the blockchain. So this is a natural application, right? I want to publish that I've generated a certificate. I wanted everyone to see it. I want to make sure it's immutable. And I want it that's replicated, that everyone's got a copy of it, that can't tamper with it. That's what you would use a blockchain for. So that's also there. Okay, so I'm going to take a 5-minute break and then go to HTTP.